The structure and interpretation of computer programs, bite size. (1.3.2) Constructing procedures using Lambda. In using sum as in section 1.3.1, it seems terribly awkward to have to define trivial procedures such as PyTerm and PyNext, just so we can use them as arguments to our higher order procedure. Rather than define PyNext and PyTerms, it would be more convenient to have a way to directly specify the procedure that returns its input incremented by 4 and the procedure that returns its reciprocal of its input times its input plus 2. We can do this by introducing the special form lambda, which creates the procedures. Using lambda, we can describe what we want as the lambda of x is lambda takes x and adds 4 to x. And lambda takes x and divides 1 and the product of x and x plus 2. Then our PySum procedure can be expressed without defining any auxiliary procedures as, let me pull up the define the procedure PySum that takes inputs a and b to be the sum of the lambda procedure x that takes 1 divides 1 by the product of x and x plus 2, and then sum that and a, and then also the procedure that takes x and adds x plus 4, and also b. So again, using lambda, we can write the integral procedure without having to define the auxiliary procedure add dx. Define the integral f a b at dx times the sum of f. So anyway, you know what it is. We just did it in the last section. Okay, so define the integral procedure taking inputs f, a, b, and dx, multiplying the sum of f, and so you're going to sum these terms here, and b. So it's going to be a divided by dx, which dx over 2, add those two together, it will be that term, and then apply lambda to x, and then x and dx will make, and then b of that will make that, taking b as input takes that as, takes that as a term and then that as a term. In general, lambda is used to create the procedures in the same way as define, except that no name is specified for the procedure. Lambda, formal parameters, body. The resulting procedure is just as much as a procedure as the one that is created using define. The only difference is that it has not been associated with any name in the environment. In fact, define plus 4 of x and then add x and 4 is equivalent to define plus 4 lambda x and then x plus 4. We can read the lambda expression as follows: the procedure of an argument x that adds x and 4. Like any expression that has a procedure as its value, a lambda expression can be used in the operator in combinations such as a procedure of argument x, y, and z that adds x and y and the square of z. And 1, 2, 3. So let's see. Okay, so it is lambda of these two arguments. So the x1, y1. Oh no, and it passes those two, that's why. Okay, 12. Alright. Using let to create local variables. Another use of lambda is in creating local variables. We often need local variables in our procedure other than those that have been bound as formal parameters. For example, suppose we wish to compose the function f of x and y, x such plus 1 ry squared plus x from y, 1 minus y plus 1 plus ry times 1 minus y. We could also express as a is equal to 1 plus ry, b is equal to 1 minus y, and f of xy is equal to r a squared plus yb plus ab. In writing a procedure to compute f, we would like to include as local variables not only x, but also the names of the intermediate quantities like a and b. One way to accomplish this is to use an auxiliary procedure to bind the local variables. Define the procedure f that takes x and y. Define f helper a and b. Add the multiple of x to the square of a, the multiple of y to b, and a and b, so times a and b, y and b, and that ends up being those three. And then add f helper to add 1 to multiple of x, y, and then minus 1 to y minus 1. It's 1 minus y. And then 1 plus the multiple of x and y is f helper. And anyway, you apply that to those. Of course, we could use a lambda expression to specify an anonymous procedure for binding our local variables. Then the body of f becomes a single call to that procedure. So define f takes inputs x and y, lambda that take the procedure that takes parameters a and b, that adds the multiple of x in the square of a, the multiple of y and b, the multiple of a and b, and the multiple, or the product, however you say it. Times all those together, and then add 1 to times the x and y together, and minus 1 from y. This construct is so useful that there is a special form called let to make its use more convenient. Using let, the f procedure can be written as define f x y let. Anyway, this is what it is. So, I'm too tired to read it. The general form of a let expression is let variable 1, expression 1, variable 2, expression 2, variable n, expression n, and then the body, which can be thought of as saying let variable 1 have the value expression 1, and variable 2 have the value expression 2, and variable n have the value expression n in body. The first part of the let expression is a list of name expression pairs. When let is evaluated, each name is associated with the value of the corresponding expression. The body of let is evaluated with these names bound as local variables. The way this happens is that the let expression is interpreted as an alternate syntax for lambda of variable 1 to variable n, body, expression 1, expression n. Now, no new mechanism is required in the interpreter to provide local variables. A let expression is simply syntactic sugar for the underlying lambda application. We can see from this equivalent that the scope of a variable specified by a let expression is the body of let. This implies that let allows one to bind variables locally as possible to where they are to be used. Let allows one to bind variables as locally as possible to where they are to be used. For example, if the value of x is 5, the value of the expression add let x equal 3 plus x, and then this term will be times x and 10, and then x is 38. Here, in the body, so basically we do this, but we change that last x to be 5. So you put 5 there, and it will be 38. Here, the x in the body of let is 3, so the value of let expression is 33. On the other hand, the x that is the second argument to the outermost plus is still 5. So this will be 5, and then these two will be 3. I see. Okay, so 33 times 5. The variable's values are computed outside the let. This matters when the expressions that provide the values for the local variables depend upon variables having the same names as local variables themselves. For example, if the value of x is 2, then the expression let x equal 3, y is plus x, so 2, and then multiply x and y, we'll still have the value 12 because inside the body of let, x will be 3 and y will be 4, which is the outer plus 2, x plus 2. Sometimes we can use internal definitions to get the same effect as with let. For example, we could have defined the procedure f above as define procedure f, takes parameters x and y, define a to be plus 1 to add 1 and the multiple of x and y, define b to be y minus 1, or 1 minus y, and then add the multiple of x and the square of a, and then multiple of y and b, and then, or the product, whatever, of a and b. And so then you add all that together. We prefer, however, to use let in situations like this and to use internal define only for internal procedures.